Welcome to Trinity A Linux kernel fuzz tester. We have Dave Jones. Dave is employed by Red Hat to manage the Fedora kernel team. And in addition to working on the kernel, he occasionally finds times to fix and break the kernel, hopefully before the users do. I'll just pass it on to Dave since we're running late, and hope you enjoy the talk.
Can everyone hear me? Yes. Yep, good. So, because we're running late, I'm going to have to go really quickly because there's a ton of stuff to get through. So this is a tool that I've been working on for probably 6 or 7 years now, but it's only really taken shape in the last 2 or 3. The basic thing it does is it fuzzes syscalls, and by that I mean it calls system calls with random arguments in random orders, so it just does all kinds of crazy things that real programs tend not to do. It's not a particularly new idea, it's something that's been around for a long time. The earliest one I could find was something against Unix SCR4, a tool that someone wrote called tsys, and what that did, it was literally just putting the output of rand straight into all the registers and calling syscalls. Fast forwarding 10 years, while I was working at SUSE, Kurt Garloff wrote pretty much exactly the same tool and ran it against Linux. And I think this is the first time someone had done this against Linux. And we found a whole bunch of bugs, really, really silly things. The problem with just calling rand, the majority of the system calls, you're just going to get enval back. So once we fixed up this handful of really silly bugs, that tool didn't really do much more for a while. A few years later, a bunch of different people started extending the idea a little. Instead of just feeding them rand, sometimes they pass, say, a file descriptor or a network socket or something like a malloc page. And this found a whole bunch of different bugs. Around 2006, the bottom one there, scratch me, that was my first sort of attempt at actually making this tool I'm talking about today. And it was just an extension of the tool that Kurt Garloff wrote. And it found a bunch of bugs, and then from 2006 to maybe 2008, it pretty much didn't do much at all because we'd fixed all the silly bugs. So coming up to modern day, almost, 2010, I extended the tool to understand a lot more parameters and types that the kernel is expecting. Completely in parallel to me and completely unknown at the time, someone at Google was writing pretty much exactly the same tool, the tool called I Know This. Does pretty much exactly the same thing, but in slightly different ways. So sometimes they find different bugs. So it's pretty neat to have 2 tools doing the same thing just to increase coverage testing. And we both stolen kind of some ideas from each other as well. It's pretty neat. So the basic how it works thing. So before you can call a system call and give it what it expects, you need to annotate every single system call that the kernel knows, all 300 and something of them. And you have to annotate every argument type, so say this is an expected length, this is an address, this is a file descriptor. And then have a bunch of routines that hand those out. So on startup, the first thing it does is create a bunch of file descriptors. It creates a bunch of network sockets. It pulls a bunch of files from /dev/proc/sysfs. And over the lifetime of the tools running, it just hands those out randomly when it wants a file descriptor. There's a bunch of other things it allocates as well, which I'll go into later. And there's a shared memory map between all the children. This is the basic, so you run the tool, it forks a main loop and a watchdog process, which I'll talk about in the next slide. And the main loop just keeps forking however many children as you have processes. And if one of these dies, it respawns another one, so it just keeps continually spawning children as necessary. This tends to need to happen because sometimes the children segfault when they call certain system calls that are just too crazy. The watchdog process keeps track of all the children, and it'll send a sigkill if it's called a system call that's stuck, like if it's stuck in a read or it's stuck in something. It does some basic sanity checks on the shared memory map between all the children, just to make sure that none of them are corrupting it and it's going completely crazy. These are the types that we know. So the most basic type we know is just arg random int, and that returns rand, essentially. argfd is a file descriptor. Arg length is a random number that looks like a length, so a lot of the time I'll just set like a high bit of a word, so it'll be, sometimes we get interesting wraparound bugs. Arg address and non-null addresses, they return things like the return from malloc, so you get a page for the syscall to scribble on. Arg pid will be one of the pids of the children. So crazy things happen sometimes when they want a PID and they all start fighting among each other, sending each other signals and all kinds of crazy things. Arg range is like rand, but it's like just a bounded range. Arg op and arg list. Certain system calls have flags variables and they want certain bits set. These are just ways of specifying those bits. Arg op is just one of the bits gets set. Arg list, a random collection of bits gets set. Arg ran page is literally a page full of just random garbage. Arg CPU is a CPU number. Path name is one of the path names that we found on startup from sysfs procfs or /dev. And then we have some other things like iovex and stock adders, which I'll go into later. So I have to keep, because there's so many different types that the system calls take, I have to keep adding special support for things like sock adders, and every time I add a new type, a whole bunch of other syscalls can then just inherit the support for that. I don't know why that isn't showing. Okay, we're going to skip that. So that was, the previous page did show a slide. Actually, what I can do, hang on a second. I don't know why that slide was invisible, so I'll just pull up the source. Trinity syscalls map.c. Okay, so what was on that slide was basically the struct at the bottom here. And every system call has one of these structs. So we have a name, which is in this case mmap. It tells it the number of arguments. There's a pointer to a routine called sanitize, which I'll explain in a second. And then there's a series of each of the arguments and their types. So it's like the adder is an address, len is len, prot is a list, and the list is all these potential flags right here. And that's the basic thing. So every system call has one of these. Put that back. The sanitize function, sanitize pointed to a function like this, where sometimes you want to special case certain things. Like for example, on mmap, if it's an anonymous mapping, you don't want a file descriptor argument, so we put a -1 in there, and we do some magic with aligning. So sometimes there's some special casing necessary, but not every system call has one of these sanitize routines. Instead of just passing rand, sometimes we just need a random number, and instead of completely random numbers, we do some really sort of weird looking numbers. And this is what I mentioned earlier, where we were trying to get like off by ones and just like really strange looking numbers. And yeah, that's basically it. And there's also some 64-bit variants of those, but they use addresses as well, including things like kernel addresses, kernel module addresses, the VDSO address. So there's a potential for all kinds of crazy things happening there. Struct fabrication. So I mentioned earlier that I annotate certain structures, like if a syscall takes a sock adder, it needs to hand one out. And it picks one kind of at random, a random network protocol. In this case, this is an IPv4 sock adder that it's generating. So it mallocs the right size, and it fills in something that kind of looks like a struct. It makes it look reasonable to what the kernel is expecting. Because what the kernel does as soon as you call a function that takes a sock adder, it validates these things and says, well, the size that you passed in doesn't match the length argument, so this is crazy, and it'll just e-inval. So you have to give this something that looks semi-viable. The only downside is this needs knowledge of every network protocol that the kernel knows, and that's a ton of work, but a lot of them have been done already. I still have some extension to do, but some basic coverage. Something else that it needs to do is be very careful about, before it calls the system calls, it has to make sure it's not doing anything that will basically harm itself, like unmapping the shared mem map between the children, for example, or anything which could just corrupt its own state. So there's a bunch of self-checks before it does the syscall to make sure that addresses are in, not in certain ranges. Yeah, there's a bunch of things we trap a bunch of signals just to make sure that they don't confuse the children. That's about it. More problems. So one of the problems I have when I find a bug with this tool is I'll report it to a kernel developing, oh, that's this problem, they'll come up with a patch, and then usually, that gets merged in the Linux tree. And a lot of the time I have a hard problem proving that the bug is actually being fixed. The reason for this is sometimes the fuzz testing takes days before it'll actually hit that. Other reasons are, if it's something like a race condition or something, it's very hard sometimes to recreate the exact circumstances. So that's been one problem that I've faced. Another problem has been over-sanitizing some of the arguments on the way in. If we sanitize them too much, then the system calls are just going to succeed and nothing particularly awkward is going to happen. So what I've tended to do in a lot of cases is I'll randomly give them the right arguments, but not always. As you can see there, that's just 1 in 10 chance. And some system calls call other systems calls, so you can syscall while you syscall, like socket call, and with these we have, it's basically, not inheritance, what's the word I'm looking for? Recursive. It's basically recursive in each other. You just have to make sure that you unrecurse properly after you return from the system call. Socket call is one of them. There was a few others, if I remember right. Another problem that it faces is after it's been running for a long time, a lot of kernel functions allocate memory on the way in, and they expect you to release it at some point. Currently, there's no mechanism in the tool for deallocating anything that was allocated, so we tend to leak quite a bit of memory. And an interesting side effect of this is sometimes we trigger the out-of-memory killer. Now, it's all well and good, but what should happen in these cases is the OOM killer should kill the actual process that's just been doing this, that's been doing all these allocations. But in some of the cases we've seen so far, that hasn't been the case. It's killed things like SSHD or send mail or something.
That's very normal for it.
Yeah.
Set up the right protection between /proc for your own SSHD.
Right, there's a score.
Yeah. It will kill the session rather than kill the child that's actually doing all of that. And quite frankly, the OOM killer is pretty stupid and it doesn't work properly.
Yeah, it's just a bunch of heuristics, and it's very easy to confuse it. So it's found a bunch of problems with those heuristics, and they've gotten slightly better as a result of this. So that's one thing that's come out of that. One of the biggest problems that I face is after hitting a bug, it would be nice if I can just reproduce that bug very quickly. And in some cases, this fuzzers literally run for 2 or 3 days before a bug has happened. So what I started doing was periodically reseeding the random number generator so I know what the seed was shortly before the bug was hit. The only problem is that it's still not guaranteed to give you a one-to-one reproducibility across 2 different runs. One problem is you may sort of, within minutes of starting the fuzzer, corrupt some state, and that corrupt state may not actually be walked over until 2 days later when you're doing a different system call. So if you're taking the seed from 2 days later, it's not going to matter because that state isn't corrupt. So yeah, that's been a big problem. Another problem is, for example, when it starts up and reads all the file descriptors from, say, /proc, no 2 runs are going to be the same because all the proc PID numbers are going to be different on 2 different runs. So I need to fix that, and I've got some ideas how I'm going to do that, but it hasn't been done yet. It's mostly, when you do 2 runs and compare the output, they're mostly the same. It's just things like it hands out different FDs right now. So what are the results of this? So last year, it found over 150 bugs. Well, from my runs. Other people have also been running this. There's a guy at Intel who has this enormous cluster of really fast machines that's constantly running this on Linux Next, and he's found even more of them, so it's definitely finding bugs. When code tends to get merged into Linux history or even straight into Linux Next, it tends to find bugs in new code very quickly. So we don't have to wait 2 days usually. Usually it breaks pretty fast. And despite what I said in the previous slide, it's usually, once you see one bug, you'll tend to hit that same bug over and over, rather than finding different bugs. As the last point says, they tend to mask other bugs, so you'll see one particularly nasty one first, and until that gets fixed, you won't get to see any of the others. And it's not just system call code that it's finding bugs in. It's found a ton of networking bugs in lots of the weirdo, like old protocols like AX25 and weird ham radio stuff. Most of those things are unmaintained and kind of awful, so it was no surprise that there was a lot of bugs there. It's found some virtual memory bugs, especially in some of the lesser used system calls. And it's found a handful of driver bugs. It's found a bunch of really old bugs. The oldest one I found dated back to 1996. This code hadn't changed at all in 16 years. If you call set sockopt with TCP options on a UDP socket, it would oops. And no one stumbled across this in 16 years. So that got fixed recently. It makes you wonder how many other bugs like that are just waiting that have been there for, going on for 20 years. Some of the VM bugs, like the mem policy bugs, they were, there's a library that actually calls these syscalls, and most people that want to do this specific functionality, they go through that library. And the library gives it the arguments that it expects. It's never going to do anything too crazy. So for 4 years, anyone could have sent these system calls garbage and just oops the kernel immediately. They were pretty bad. That was the case of something like a switch statement, and the default case was a bug, so it would just panic. Yeah, that was pretty terrible. And yeah, the VM in distress, I mean, because the leaking thing I was mentioning just now, it tends to find a lot of corner cases in the page allocator where, especially after a while when it's fragmented kernel memory, if it's been running for 2 days, your chances of getting large allocations drop dramatically. So when people want to do things like 64K chunks of contiguous memory, it's pretty unlikely it's going to happen once memory's been that fragmented. So there's been a load of those bugs is found. We had a security fix in one of the system calls, and while we were preparing an update for one of the Fedora releases, we were running this tool on it, and I thought, well, let's tell it to just do that system call that just got patched. And within an hour, it actually found another problem. So it was a security fix that actually needed another security fix. Lots and lots of error path memory leaks. I mean, a lot of this code just never gets tested. It's and it's not just memory leaks, it's things like missing unlocks in error paths. Error paths are just very poorly tested. The bottom example there, broken locks, when someone removed the big kernel lock from all the network protocols and replaced them with spin locks, there was a case where all you had to do was mod probe a certain network protocol, or even just create a socket with that protocol, and it would oops immediately because there was an unbalanced locking thing. Just from mod probing the module, so that had been patched, and clearly no one had ever even mod probed the module afterwards to test it. There's some really scary things that is found as well. My previous laptop, actually the second part, I'll go with the first one first. Sometimes when I see a bug that looks too weird, until I actually see the same bug on another machine, sometimes I'm actually questioning whether the hardware is at fault or it's actually a real bug. Because there's definitely been some cases where the CPU has been overheating, or there's just been some bad memory or something. And those kind of things tend to show up very quickly when you're running stress tests. The second problem, SMI handlers. I had a laptop that, when it gathered all the proc files and what have you on startup, one of those was one of the ACPI files to read the current battery state. And when you read this battery file, it triggered an SMI, system management interrupt. And there was something terribly wrong with this SMI code. It's all completely invisible to the OS. But the long story short, the battery died. If you kept reading the same file fast enough, the SMI handler, I think, just couldn't cope with that flood of interrupts, and well, bad things happened. So that was actually still under warranty, so I got a battery replacement, and then I did it again. And that confirmed my thesis that it was actually, this was what was happening. So yeah, I destroyed 2 batteries. So I don't recommend always running it on the laptop, even though I'm about to do that at the end of this, just to demo it. Not just kernel bugs. This is a real fun thing. So this parameter here, -c execv means just call execv and no other syscalls. -v is a feature I call victim files. And I came up with this idea because I wanted to do things like, what happens if I have a bunch of files, say, on an NFS mount, and instead of reading file descriptors from /dev on startup, read them from the NFS mount, so then we do some weird stuff with NFS. That was the original intention. But just for fun, I decided to feed it /bin one time, and this is what happens when you do that. Execv. So what you should be watching is the bottom window. All these things that are just randomly segfaulting. These are, whoa. Let's stop that. So if I now do file temp call, that's just from like a 30-second run. All these things just segfaulted. And it's calling execv on these binaries with just garbage as a parameter. So it could be just incredibly long parameter and it's overflowing it. They all tend to be pretty much the same kind of bug, but yeah, everything /bin is terrible. So that was a fun sort of thing that I wasn't expecting to happen, but yeah, it did. Yeah. So that's the kind of thing that it does now. So one of the, it's a lot of work just maintaining what I have so far. So every time a new system call gets added upstream, I have to add support for that system call. Only 10% of the system calls that I currently have sanitize routines. Some of them could probably use at least a basic one. They're not always needed, but sometimes you can just improve the chances of the system call getting further into the function. More struct fabrication, like the sock adder thing that I was doing. There's a whole bunch of different types that the kernel is expecting that we just don't, right now it's passing garbage rather than realistic looking structures. And things like that sock adder struct fabrication, that needs even more extension for finishing off the remaining network protocols. There's only a few left, like Bluetooth and a few others. And every time a flag gets added to a system call, I have to add that to the relevant flag lists. More fun things that I want to do is, right now, if you give it no parameters, it'll literally call these system calls completely in a random order, and no realistic program actually does this. What I would like to do is an idea I call system call chains, where patterns of what realistic programs look like. They do, like they open a file descriptor, maybe they read from it, maybe they close it. So I have a chain of 3 different system calls there, and I do these little clusters. And that's something I'm going to experiment with just to see if that makes anything fun happen. Destructors is something I need to happen for all the allocations so we don't leak so much memory when we run. And root mode. There's a bunch of system calls that will just, you'll get EPERM as soon as you call them because they only expect to be run by root. Some of them you can't really fuzz because things like shutdown, well, you're going to fuzz it and then your laptop will shut down, so that's going to be pretty pointless. But some of the others will set up some kind of state that only root is allowed to do. That's something that we could possibly get into. And ioctl. I cannot say enough bad things about ioctl. So right now, the support for the ioctl syscall is pretty lame. It doesn't do a huge amount. It's not going to really find any bugs with what I have. The problem with ioctl is just it's a terrible interface. The bits highlighted in red there, as you see, the second argument is a device-dependent request code. So the request, if we fabricate one of those, we have to make sure that actually matches the right file descriptor. And they can be shared between different types of drivers as well. The third argument, it could be anything. We have no idea what that is until we annotate every single ioctl or the ones we care about. So what I've done with syscall so far for the last few years, I now need to do with all the ioctls. So that's a massive job that I've been putting off, but I'm going to have to get around to that soon. The last point, it's similar to the struct fabrication for things like sock adders. ioctl takes these just opaque structures, and I'm just going to have to manufacture something that looks kind of like one of those for every single ioctl. Awful interface, don't use it. So that's pretty much all the slides. So I showed you the fun user space thing. So if I just run it with, no arguments, actually it's so quiet. So what we see here, it starts up and creates a bunch of sockets, and now it's looking for files in /dev, and it's found 25,000 files in proc. And there it goes, it's running. So it's thousands and thousands of these are happening, and there's crazy stuff going on down here already. I don't know what's all this. Oh, that's from before. So as it's running across various network protocols now, these are being loaded, so it's just triggered the VLAN support. That's probably just going to keep running. Oh, it's done there. We just try to do an allocation bigger than what kmalloc can actually do. Yeah, so I think I'm just going to leave that running, and we'll see what happens, and I'll take questions while that's doing its thing. Okay, 10 minutes. Willie. What about fcontrol?
Well, it's another one of these. fcontrol is another one of these ridiculous multiplexing one. I was just wondering if you add support for fcontrol as well.
Yeah, actually, off the top of my head, I don't remember what I've done so far, so let's take a quick look. Because, as Willie points out, fcontrol is another multiplex system call, so yeah, it's very basic. It literally just picks a bunch of the flags and just feeds that down. Probably not going to do a huge amount of interesting things. Fix me needs to mutate some. I don't even know. So yeah, that's fcontrol. Needs work. James?
So you mentioned the crazy guy from Intel. Are there any plans to integrate Trinity into Wu-Feng Wang's massive?
Wu-Feng Wang is the crazy guy from Intel.
I know. So are you planning to integrate it into this? Because I haven't seen any Trinity.
That's what he uses.
So
He's using this already.
my subsystem of hatches will Trinity compliant.
Maybe. Or maybe I just haven't done the SCSI ioctls yet. I'll come back to you. Go ahead.
How do you deal with hot hardware that you don't have? The world's full of drives and hard drives.
How do I deal with hardware I don't have? The bugs that it tends to find is the generic code that's not device-specific. For hardware-specific things, it literally is whatever it finds on the machine it's running on. So, like if a certain bug needs, a Bluetooth interface to be brought up before, it's going to trigger that bug, it's only going to happen on, obviously, things with Bluetooth hardware. So, Badly, I guess, is the answer to your question. There's no real good answer. Virtualization is kind of, it would be nice if there was, a suite of virtualized devices and I could just pull from those, but they tend to only emulate, a handful of devices anyway. Go ahead. Oh, sorry.
I have a microphone. So oddly enough, with a database server, we do funny fuzz testing, and we've got to the point, there's two bits that may be useful to add to this, one of which is we have a random query generator that you give a grammar to, so you instruct sort of what parts of stanzas of queries and what types of queries and what frequency to do, and then you have a program that then generates queries that fit this grammar. So that may work with the idea of chaining syscalls, basically then writing a grammar and then columns, and you can adjust sort of frequency and what in order and have other snippets to that can get a bit generic, and then you have the whole art form of actually writing those grammars. But they've found it pretty useful for us to especially interrogate specific parts where it's like, okay, now try join, or something like that.
What database is that?
It'll actually run about on anything. The project is called RanGen.
Okay.
Yeah, I can.
Can you give me a pointer to it later?
Yeah.
Thanks.
And the other part it does is because MySQL specifically was so damn buggy and segfaulted all the time, the QA guy writing the code got sick of filing bugs with longer things, so wrote stuff to do sort of automatic bisecting down to the minimal sort of test case, and then because you could trigger it like, when it core dumps, it's it. So maybe you can start to.
Yeah, the guy at Intel who's running this on some huge cluster is doing something like that with the bisecting.
Yeah.
It's very useful.
Yeah.
Oh, yeah. So this is kind of verbose mode. So you can see it's actually, these are the system calls it's actually doing, and the various arguments. It's kind of there mostly for me to sanity check what it's actually passing down so I can take a look and make sure it's not doing anything wrong. So just leave that running. Next.
Yeah, David, you mentioned the complexities of ioctl and so on. One of the things you might be able to take advantage of is the fact that the ioctl definitions themselves actually have the structure that's passed to them in the definition of the ioctl. The IOR or IOWR defines, give the number, the identifier, and then the struct that is supposed to be passed to it. So you should be able to parse the actual header files that define all the ioctls and work out what the structure is actually passed to as that completely untyped void pointer.
I still stand by my assertion that it's an awful interface.
In the kernel, I think that there are probably more bugs in the drivers. And, for example, network drivers, we've had major problems with the bonding driver with 10 gig and BE2net driver just locking up. And I guess that fuzzing input to drivers somehow would be some kind of wonderful thing if it were possible to actually generate some kind of random input to these, particularly network devices, because it
comes back to the same problem. All these interfaces are all ioctl based. So once I have some basic structure for fuzzing ioctls, this should just fall out. Anything like when you, for example, if you mentioned bridging, just creating a bridge is like 3 or 4 ioctls when you pass, the interfaces in, and it. So once I've got bonding, sorry, not bridging. So it should just eventually happen. It just needs to sit down and write the code. I hope.
So you mentioned that you found bugs like missing unlocks on error paths and things like memory leaks. Is that something you're auto-detecting, or are you observing that while the tool is running?
The bulk of them actually were found by another guy who was running the tool, and he was using the kernel's memory leak detector. If you boot with kmem leak equals on, as long as you built that in, then it maintains a list of allocations over time. And he ran it for a while, then killed the fuzzer, and then saw what was still, unreferenced and actually leaked.
Missing unlocks, are you finding that through things like software?
Yes, LockDep is finding all the locking problems. That blows up very quickly. Okay.
Sorry, I've got a really simple, stupid question, but if you do come across something which totally kills the machine, what logging have you got to find out what that was?
The only time I've actually had bugs where it's completely wedged the machine, I've usually been able to get something out over serial, so I managed to get a trace. But thankfully, those bugs are few and far between. Another thing that's been useful is there's a kernel option called page alloc debug, and sometimes that finds a lot of those bugs, and you'll get an actual oops or a GPF rather than a locked up machine. One more.
So you normally run this as, you said you have your root mode. Normally it's run as a normal user to avoid hardware destruction, or, I mean, I can imagine random syscalls all over your disk could be a little...
Yeah, bad idea. Really bad idea to run it as root on a, unless you're running it in a VM, which there's actually a guy at Oracle that's how he runs it all the time, as root in a VM, and he finds all kinds of crazy stuff. A lot of them are kind of, your root, you can do anything. You know, you've got a gun, you're just blown off your foot, essentially. But some of them are, I mean, there's in no circumstance should the kernel oops, regardless of what user you are. So, yeah, some of these are real bugs.
What happens when some process goes to sleep, for example, waiting for data in a pipe or similar? Is it get killed or waits for random wake up?
We send a sig kill, but if it's blocking, then it's just going to, you know, it's not going to wake up because it's in D state. So there are cases where it will actually just eventually wedge if everything ends up in D state. I've tried to add some code to actually prevent doing things like that. So if one process reads from a file descriptor and then gets wedged, I blacklist that file descriptor and say don't read from this again, because that's likely to lock us up. So there's a few little self-defense measures like that. But yeah, the watchdog is actually, that'll just send kills when it thinks something hasn't, if it hasn't made any progress and hasn't made any further system calls in 30 seconds, it'll send a sig kill.
Some of us happen to believe that is in itself a bug, that a process should always be killable. But
wouldn't it be nice?
That's a giant fight that perhaps we don't want to have right now.
It would be nice. And things like NFS servers going away and everything just wedging, yeah, that would be nice to have solved.
I do have a partial solution.
Okay, that's all we have time for. Thank you, Dave, for the talk.
Thanks.